In this video, I will be presenting the PCB design, so both the schematic and the PCB layout for the main board that we have been using for the avionics of ERC 2023 for the Kerby project. So you can see here the PCB that we have been designed and used for the competition. I will walk you through every part of the PCB. And first, let's have a quick overview of what this is. So this is an STM32 based microcontroller. So this is the microcontroller here in the middle. And this PCB is designed in a way so that it is as modular as possible. So we can connect multiple boards on top of this PCB and attach them to these connectors that I highlight in green here. The PCBs are connected to each other through a CAN bus. So we can have multiples of these PCBs here, and they can be daisy chained through this bus. So we could have a connector, a cable that goes here, then it comes out here, it connects to the next PCB, and so on. And we can do it on both sides to have some redundancy. This PCB here has multiple interfaces, so it can be connected through USB to UART, so we can log some data. Every connection here to the external PCBs can be delocalized using these connectors. We have an external electronics fuse for protection here, and also an external flash, which we use to store the firmware on, so that we can have more memory to store data and also to store like the whole program. Being in a CAN bus, we have a dip switch here, which can be used to change the node ID. So we can set a unique ID for each of these PCBs, which makes it possible to communicate with each PCB individually. Then we have these switches here, which are used to set the termination resistor of our of our node, because in a CAN bus you will need to set a termination resistor at the first and last nodes for the bus to work. So I recommend you to read a bit on the CAN bus. Then we will have here some other connectors. So this one is used as a power connector and is interfaced with another PCB, which is used as the power source for this PCB. So the PCB here, the board, can be powered through either the USB port or through this connector, which is interfaced with an external PCB. So this is the gist of how this board is designed. And now let's get into the more technical stuff and how the schematic is, as well as the PCB layout. All right, so now onto the hardware side of the project. So the hardware, as usual, is divided into two parts. So we have the schematic design in this file here, and we have the PCB design, which defines all of the electrical, the physical layout of our PCB. So let's look first at the schematic design. So when you open the schematic, the first thing we'll see is the overview, which just describes the different blocks of our design. So I would go through each of them quite fast so that you can have a good overview. So first, the MCU or microcontroller defines the main schematic block, which defines all of the connections that we need for the different communication protocols like SPI, I2C, or different GPIO buses like general input-outputs. And we can also have some control pins like controlling the CAN bus type or mode, and also controlling some power outputs. There's also a connection to a USB to UART bridge. So this bridge here is used for debugging purposes, but also for logging data or displaying debug messages. So I will present this later on. It's also connected to, of course, the power connectors, which are used to power the board, but also to interface with another board that I will be describing later. Then we have the node-to-node connectors. So these connectors are used, as the name implies, to connect different nodes together. So as I've explained in the overview of the electrical system of Kerby, we have different nodes and different microcontrollers which communicate to each other with the FD-CAN bus. So we have two FD-CAN buses. So this is for a redundant network. So this is very useful because it ensures that communication is kept even if one of the buses fails, so that we can always have some information going from the microcontroller and from the network of microcontrollers to the Jetson, which is our main computer. Then we have the flash memory, which is used to execute code from the external flash memory. So this is an external QSPI Flash memory. So this is because the main microcontroller doesn't have a lot of flash, and because our program is quite large, we really want to have some way to offload all of the data and the program to an external flash so that we can have more room for other things. Then we have the node to HATS connections. So as I've explained in the overview, this microcontroller can really interface with different PCBs, different sensors, and these sensors have a very special shape, and there are three HATs that we can connect to this board. So this is why we have three sets of buses here, which I will explain later in this video. Finally, you have the mechanical elements, and these are just test points or mounting holes, and we also have the logos because I didn't really know where to put them. So yeah, so this is the overview, and now of course we have some more details in the text here. So I have the definition of the microcontroller, the different interfaces that we are using, and also the creation date and the version. So this is the fourth version of the board. So this is actually the board that we used for the competition. All of the interfaces are working, and I will maybe later in the video explain what type of improvements could be made and what we really want to improve on for next year. All right, so now we will first look at the MCU sub-schematic. So we can either go inside that block by doing a right click, enter sheet, or you can also click on that number here. So this number just is linked to the page number. So here this is page 2 out of 11, and it defines the microcontroller schematics. So I will now go into detail into each part of that schematic so that we can really understand how things work. So first, what are these two blocks? So we have a first block here, which defines all of the GPIOs and all of the connections of our microcontroller. So the microcontroller, if you look at the data sheet, so you can just press D after selecting this component. If you look at the data sheet, this opens a new page here. You can really look at what this whole thing is. So this is basically a chip. Just remove the dark mode. So this is basically a chip with a certain amount of pins, and each pin has a certain function. And you can look at the function and at the pinout, like this is a physical pinout of each pin. And you can look at the function of the pins here, for example. So in our case, we are using an LQFP100 package. This means that there are 100 pins, and each pin has a certain function, as you can see here. So we've defined this schematic, this symbol here, such that each pin number here corresponds to the correct pin name and also has the correct function. So, for example, let's look at the I2C bus. So in this case, we're using pins 92, 93 which correspond to the PB6 and PB7 pins. So the B here corresponds to the port, because each of the pins have different ports, like the E port or the D port, the C port and the B port, and so on. So now let's look at the schematic. At the data sheet. So if we do just Control F PB6, we can look at this part, and we know that PB6 corresponds to the pin 92 in the case of the LQFP100. And this PB6 has multiple functions. So in our case, we decided to use it for I2C, but we can also use it for other functions if need be. So this is one of the examples. So the same was done for every other pin. So why is there also two different blocks? This is because I've decided to like separate the microcontroller into its pins and into its power inputs. So now let's go into each definition quite fast. So these two control pins here I used to interface with another microcontroller, another, not microcontroller, but another PCB, which is actually the power, the control, the board which controls the power of our main microcontroller. And this allows us to control two outputs, so a 5 volt and a 3.3 volt output. So I can also show you actually how this looks like. So if I open the project, so this is the project that I am working with, and there are two projects. So the Orion PCB is the project that you see right now, and there's the Orion Power here, which is the board that actually powers this board. So let's look at the PCB of that board just so you can have a better overview. So this is the board that will be connected onto the main board, and the 3.3 volt, the 5 volt CTL and 3.3 volt CTL pins can control the output on these two connectors, so that we can control a 3.3 volts and a 5 volts output. All right, then we have the FDCAN1 status. So this is basically just for controlling an LED. So let's look at this board. Like this is the main board that you are looking at, and this will just control two LEDs here. So one for the CAN1 and one for the CAN2, and this is just a way to really have an indication of the bus status. So after that, we have the CAN1 silent pin. So this is not very useful, and we won't use it actually. You can look at the data sheet, and I will explain it in more detail later, maybe. We have the 3.3 volt status. So this is just a pin that is used to see what input we are using. So I will also explain this in more detail in the power section of the board. After that, we have the QSPI pins. So what is QSPI? This is a protocol which is used for interfacing with an external flash memory. So as I've said before, we really want to have an external flash memory so that we can put the firmware on it and have some room for other things. After that, we have an, how do you call this? This is a dip switch module. So this dip switch here allows us to select the ID of the board. So the ID will be used in the CAN FD bus for selecting to which board we want to send the data to. So we have multiple nodes, as I've said, and each node will have its own ID, which is selected from this dip switch. So you can see that the dip switch is here. And this with this dip switch, we can really give a unique ID to each board and communicate to each board individually. Then we have the FDCAN, RX and TX. So this is just for the node-to-node connections. So you can see them here for the CAN1. So this is this will be linked to a transceiver and then to the microcontroller for the CAN bus. Then we have, of course, LEDs. So we have control LEDs for example, the yellow LED and the green LEDs. This is just for displaying some information, some visual information. So in our case, we use the green LED for a blink LED, so that we can see if the board is alive or not. And we use the yellow LED as debugging purposes, so it starts to blink, or it blinks whenever a new sensor is connected. So this allows us to see if a sensor is being constantly disconnected and reconnected. So if that happens, then this LED will be blinking. And then we have, again, this is similar to the 3.3 volt status, but for the 5 volts one, and I will explain it in more details in the power section. Afterwards, we have some other definitions for the pins. So these are used in the node to HATS connections. So I will explain this also in the HATS section, of course. And this is also, all of these are used really for the GPIOs and the connections to the different PCBs that would come on top of this PCB. So all of these pins are linked to these connectors here. So then we have the I2C buses, which are also linked to some of these connectors in green here. And yeah, so this is the main GPIOs. And then we also have, of course, crystals. So for this project, I am using 2 crystals. So we have a low frequency crystal and a high frequency crystal. So these are used because we wanted to have the best possible tolerances and the highest stability in our crystals. And using an external crystal really allows us to have very tight tolerances for the frequency, which is very useful, especially in the CAN bus, which really needs very tight tolerances, especially for the high frequency crystal here. So this low frequency crystal runs at 32 kilohertz, while this one runs at 48 megahertz. So this is very fast. Okay, so the power section now, we have all of the power pins. So these power pins, again, were defined according to the datasheet. And we have the standard, very classic decoupling circuit. So each of the power pins will have its own decoupling capacitor. This decoupling capacitor needs to be as close as possible to the pin, to the relevant power pin. And the same can be said for the VBAT pin. And then for our analog VDD, so VDDA, and the reference voltage, we have also very standard decoupling circuit. So we have a small decoupling capacitor very close to the pin, and a larger bulk capacitor, which is a bit further away from the pin. Then we have a ferrite bed for some filtering, and another decoupling capacitor, another bulk capacitor, which can be a bit further away. So you can see some, I've written some references for some of the circuits. So this is just a reference note, which you can check if you want to have more details about these types of circuits. And then we have some other decoupling capacitors, which need to be placed close to the VCAP pins. So this is just according to the datasheet. So this is just me following the datasheet. Of course, then we have the ground pins. And I forgot to explain how these capacitors were chosen, but it's a fairly complex calculation, or not very complex, but something that you need to look into. So you have what is called a critical transconductance that you can compute with these formulas. And for the STM32, we want the ratio or the gain margin of the GM and the GM critical to be larger than 5. And we also need to satisfy this condition. And all of these conditions will depend on multiple factors, such as the load capacitance, or also the series resistance of the oscillator. And after doing all of the computations, you can find a suitable crystal. So in our case, a suitable crystal would be the one that I've defined here, which is this model. So I will put a link in the description to the report here, which I wrote for a semester project, which defines some part of of this PCB. So this was for the second iteration, which was about 8 months ago. So there were 2 more iterations after this one. So it is a bit outdated, but will be used, could be used later for reference. We also need to have the reset circuit. So this circuit here is used to set the microcontroller either in the bootloader mode or in the firmware mode, you could say. So this is just a switch, an SPDT switch, or single pole dual throw switch. So just your standard switch, which is connected to the boot 0 pin. So this pin here can be seen, this switch here can be seen here, and we can really set it either in the firmware mode, so on this side, or in the bootloader mode. So we won't really be using the bootloader mode, but I put it here in case there is further development down the line. Then we have our reset button, and we have some very small decoupling capacitor just to avoid spurious resets. And this is just connected to our reset pin. So this is a very standard circuit here, and there's nothing really special. So we now go onto this section, the debug section. So you might wonder why I have the reset label here and the NRST label here, and they are not connected. This is because we're also using this debug section, and this debug section has here the debug connector. So first, what is the debug used for? So this is used for debugging the board, as the name implies. So if you are working with Arduinos, you know that usually what you do is you just connect the USB port, then you write your code, and then you flash the code onto the Arduino via the USB. So this is what is called DFU, or device firmware update. But it doesn't really allow us to have a lot of control over the program. So it's very hard to stop the program or to put some breakpoints or analyze the state of the variables. So in our case, using a debug connector and an external debugger, we can really connect an external debugger. So in our case, I am using the ST-Link V3 Mini E. So this is a very small debugger that you can see here, and this connects to this port here of the microcontroller of the board. So if you look at the 3D model, it will be connected to this part of the board, and we can really use it to inspect and flash our program and have a lot more control for debugging purposes. So there is a diode for protecting the ground and the VT-ref pins. So this is just a standard diode which will protect against the voltage spikes. The interface is also ESD protected. So ESD is electrostatic discharge. So this also can protect against voltage spikes. We then have some fairly small resistors. This is just for limiting the current to the pins for further protection. And there's also another GST connector for debugging, just in case we don't really want to use this one, but we want to have a more durable connector. So this is an optional connector. Finally, we have the different buses, which will be connected to the different parts of the circuit. So the I2C and the GPIOs and SPI will be connected to the hats, or the different PCBs that will be connected to this board. The FD-CAN is used as node-to-node interconnects. Then we have the MESA connectors. So MESA is the board that I talked about before, so this one. And after that, we have the UART connector, which is used for the USB to UART bridge. And finally, the QSPI, which is used, of course, for the flash. All right, so this was the overview, a fairly detailed overview of the microcontroller part of this circuit. All right, so now that I've talked about the microcontroller part, we'll now go on to the USB to UART bridge part. So what is this used for? So as I've said, this is used for debugging purposes. So it will convert the UART protocol to the USB protocol, and this will really allow us to print messages onto a serial terminal and have some more information about what is happening inside of the board in case we don't have a debugger. It is also used for sending data in a very special format so that we can use it for calibration, for example, IMU calibration or logging data. So let's go into that schematic. So you can just press on that or click on that small number here. So this is the schematic that we will see. It's a fairly simple schematic. So we'll be using the CP2102N chip. So this is a very widely used chip, and just have to take care, like to pay attention to the version. So we are using the N version, which is the newer version. So if you look at the schematic or at the PCB, at the datasheet, I mean, you'll see that the circuit that is needed to make it work is quite simple. So it already has a lot of things inside, which really allows us to use it and abstract all of the USB stack and other programmation that we would need to do if we didn't use this chip. So this is a very useful chip, which does all of the work for us. So now looking at this schematic, you can see here two LEDs. So these LEDs would be used as status LEDs. So they are connected to these two pins of this chip. So the function of these pins can be configured through the Express configurator. I think that it now changed name, but I will put in the description of the video a link to the software that is used to configure these pins. Then we have, of course, the communication pins to the microcontroller. So we are communicating to this chip with UART1 and so UART1 RX and UART1 TX. You just have to take care that TX is connected to the RX of that chip and the RX of the microcontroller is connected to the TX of the transceiver chip. So afterwards, we have the power section. So we have the VBus, which has to be divided from the USB voltage, and we have the VREG in VDD and VIO, which need to be powered through a 3.3 volts output. So looking at this part, you can see that we have connected the shield and the ground together. This is just to simplify the circuit. We then have a fuse. So this is a 075 fuse, which means that it's a 750 milliamps fuse. So you can look here at the... Oh, actually the datasheet is now not available, but you can look, if you look at the name and you just type it onto Google, you'll see some of the specs. So let's go into Mauser. Normally, you can see here that we have 1.5 amps tripping current, and this is a 750 milliamp holding current. So this was chosen because the USB standard, at least for a normal USB, is limited to 500 milliamps. So we chose a bit higher than that so that it doesn't trip accidentally. And this really allows us to have some very crude protection, but should be enough for our application. We then have a bidirectional diode here, which is used for against transient spikes. So you can also look at the data sheet. And so yeah, there isn't a lot of information, but yeah, you can see here what is used for. So this is used against voltage transients, and being a bidirectional diode, there is a symmetric characteristic to our voltage to current curve. So this is very useful, which means that it will clamp the voltage for both positive and negative spikes. After that, we have a PMOS MOSFET. So this is used as a reverse voltage protection device. So in reality, it's not very useful in the sense that this connector should not, like it is impossible to plug it in the wrong way, but we put it just in case, and it is a very small component. So this is just as another layer of protection. Then we have an ESD chip. So this ESD chip is used for the data lines of our USB connector. So it has to be placed as close as possible to the USB connector. And then this voltage here, so this is 5 volts. The V-bus from USB is 5 volts. It goes inside of an LDO, which converts the 5 volts to 3.3 volts. So as is written here, we chose to use an external LDO and not the internal LDO from this chip, because there were many reports on the internet saying that the internal LDO was not very good. So this is why we chose to use this LDO. And in this schematic, you will also have to take care about the capacitors that are on the V-bus line, because the USB protocol has a very limited, maximum capacitance that can be put on the V-bus line. I think it is like 10 microfarad. So we chose an LDO which has a fairly low capacitance requirements on the input and outputs. And then afterwards we have, of course, two decoupling and bulk capacitors. So these are used just for this chip, and we just followed the datasheet for that. All right. So, also another detail. So this is not critical, but it is a good practice. So we used a differential controlled impedance pair for the USB line, but I will explain this in more detail in the PCB design section. Okay, so now we will go onto the power connector section and power circuits. So as usual, you can just press on this button here and we'll see this part of the circuit. So first, let's look at this section. So here we have just the connector. So this is the connector that will be linked to the main power circuit. So this connector here will be connected to this connector here. And this board here that I will explain in another video converts a power input from the power supply to 3.3 and 5 volts outputs, which are then connected to this part of the circuit and powers the whole board. So now let's look at the schematic. So we also have, as I said in a previous video, in the previous section, the 3.3 volts and 5 volts control pins, which control the output on these two connectors. So let's look a bit at the power path. So the power path section is the section that controls which input voltage and input source we are using for our microcontroller and for our circuit. So for each voltage, like 3.3 and 5 volts, we have two possible inputs. So we have an input from the Mesa board, which is this board here. So this board here, to give some context, takes as an input like 24 volts, then goes through a double buck converter. So this is a switching regulator, and it outputs 3.3 and 5 volts as a switching voltage. So a switching voltage is a voltage that is a bit like a seesaw pattern. And so it is not very well regulated. Like, it's not the flattest possible voltage, but it is very efficient and can deliver a lot of current. So this is why we're using an external PCB here. So this is the EXT sources for the 3.3 volts and the 5 volts. And we have another source. So in this case, this is the VIO. And in this case, it's the VBus rev voltages. So as a reminder, if we look back at the USB to UART section, the VIO here is connected to the output of our LDO that is connected to USB. And the VBus rev is the input of the LDO. So this is 5 volts from the USB. So basically what that means that each of this chip takes as an input a low power but well regulated voltage. So this is on VN2, and it also takes a high power but a bit more noisy voltage on the VN1 input pin. So what does this chip do? This chip is what is called a power multiplexer, so power mux. And what it does is it basically takes two voltage inputs, and then depending on a resistor divider here, which we can set, so we can choose the resistors. Depending on this, it will switch automatically from this voltage to this voltage, depending on the truth table of that chip. So now if I look at the truth table, we can look at the different switching conditions. So in which case we'll be using VN1, and in which case we'll be using VN2. So I won't go into too much detail, but what you should know is that these resistors here were chosen such that we will have a 2.87 volts of switching voltage threshold. So this basically means that the external voltage here so this is the high power voltage. So this chip here will use this voltage until it reaches 2.87 volts, and then it will switch to this voltage. Of course, this is if the two sources are present. If only one source is available, then it will use this source. We then have a MOSFET here. So this MOSFET here is just used for controlling, like manually controlling which source we want to use. So this is quite useful in case we want, for example, to have a very well regulated output, because some sensors, for example, need a very well regulated 3.3 volts, and we don't really want to use this less well regulated output. So this can be useful in this case. So the same can be said for the 5 volts part. So in this case, we don't have this MOSFET here, and we also don't have the resistor divider. So by connecting PR1 to VN1, we basically say that we want to prioritize the high power circuit. So why did we do that? This is because the 5 volts in most cases is used for powering like very powerful or more power hungry peripherals like servo motors or LEDs. And as I've said in the previous section, the USB port that we are using can only provide up to 500 milliamps of current. And if we try to get more than 500 milliamps, then there could be some damage done to the circuit. So by giving priority to the 5 volts input, like the high power one, you can ensure that in most cases there will be no issue, like no damage done, because we will be using the high power part of the circuit and not trying to pull current from the USB port when there is not enough current. So this 5 volt status here is used to check whether we are using the high power circuit or the power from the USB input. And the same can be said for the 3.3 volts status. We then have two bypass jumpers here. So these are just used in case we have some damage to the chips last minute, and we really want to bypass this selection circuit so that we can still have something working, just even if one of the chips burns. So we can see these jumpers on the back here. So now we have another addition to this version of the board, which is the 500 milliamps electronics fuse. So this was an addition that is only present in the V4, so the fourth version of the board. So this electronics fuse is basically a fuse that is controlled electronically. So all of the computation for the resistors were done according to these design parameters. So we want an under voltage voltage of 2.7 volts. We have an over voltage threshold of 3.8 volts. So these were computed from the by looking at the absolute maximum ratings, so that we can really stay within the absolute voltages of the chip in all cases. We then have the maximum current that we want going to the chip, and then we have other parameters. So from these parameters, we can then compute all of the different resistors. So you can just look at the data sheet again for the computation of the resistors, but it is also defined in a spreadsheet that I will show you shortly. So here in the data sheet, for example, if you type calculation, you can look at the different computation and calculations for the different resistors, the different slopes for the slope control, and all of the power dissipation and stuff. So a lot of this can be simplified just by using the provided calculator. So I will now show you this calculator. So if you go into Node PCB, Orion PCB, MISC, there will be here a calculator, so design calculator. And if you open it, you can see all the different automatic computation that is done according to the design parameters that I set previously. So this is a very simple way to compute all of the parameters, right? So what this chip does is, of course, is that it will cut the power and automatically recover it if the 500 milliamps is exceeded. So if you look at the PCB, but I will give more detail later, you can see that the 3.3 volts plane, or the power plane here, is divided into a power section, like which covers the whole board, but is also divided into a part which is only under the microcontroller. And the thing that divides these two parts is the electronics fuse. So this really allows us to be sure that we will not exceed the absolute current ratings of the MCU. Even if we short a pin on the microcontroller, it will only pull 500 milliamps at most before the fuse triggers. Okay. So the 500 milliamps was chosen looking at this absolute current ratings. So yeah, so this is for this section. So now we will move on to the next section. All right, so let's move on to the node-to-node connectors. So the fourth version of Kerby, of Orion, which is this board, uses the FD CAN bus for communication between the different nodes. So now let's look into what this looks like. So for each of the board, we'll have 4 connectors. So this is because we are communicating through 2 CAN buses for redundancy. And we want to have 2 pairs of connectors so that we can daisy chain the boards. So we can put one board after the other and connect it one after the other from board to board. So I can have one board like this, like this one. Oops. So I can have one board like this. Oh, I can't really. Right. So I have one board like this, connect another one through these connectors, then another one through these connectors, and we can really daisy chain them one after the other. So we then have a protection circuit. So this is against voltage transients. So looking at this chip, we can look at it and see that it is meant especially for the CAN bus and CAN FD bus protocols. So this is very important to choose chips that are meant for the application. This is because all of the different applications will have different requirements, like rising edge requirements or capacitance requirements. And choosing this chip, we can ensure that it will work and will keep the signal integrity of our CAN FD protocol. So we then have two capacitors here, which are set as do not place, DNP. So this is just optional filtering capacitors. So I've decided not to place them to not affect the rising edge time, the time for the rising edge of our signal, to have a faster switching rate. We then have this SPDT switch. So this is a switch that is used to set the termination resistor of our CAN bus. So if you are familiar with the CAN bus, you know that each of the nodes will be connected to two wires, which are the CAN high and the CAN low. So in our case, we put plus and minus. And at the beginning and at the end of the network, you need to have a 260 ohm resistors or 120 ohm resistors to terminate the bus. So termination resistors are very, very important to ensure that we don't have any signal reflections and that the signal, the integrity of the signal, is kept throughout the whole network. So in our case, we use a split termination, which also serves as a low-pass filter to our network with this capacitor. So this is a recommended practice for the CAN protocol. So this switch here can, by switching this switch, will either connect the whole termination resistors or disconnect it. So this switch can be seen here on this PCB, on this part for the two buses. So we will need to set this switch to the termination position for the first and the last nodes. So in our case, the first node will be the Jetson. So there will be one switch here on the Jetson on another PCB that I will present, and also on the last node, which will be on one of these boards. Okay, then it goes through a common choke resistor. This is for filtering some higher frequency noise and for filtering common mode noise. So this is just an inductor, and it is placed in line with the CAN high and CAN low lines. Then goes, of course, through our transceiver. So this is an FD CAN transceiver, and you have to make sure that each board has the same transceiver to be sure that we have the same timings. Well, I think this is not necessary, but we've observed some discrepancies when using different transceivers because we had different timings. So we use this TCAN 1051 chip. So this is an FD CAN transceiver chip. So why do we need a transceiver in a CAN bus? This is because these voltages here, which come from the microcontroller, will be 3.3 volts or TTL voltage, which is directly output by the microcontroller pins. It then needs to go through this transceiver, and the output here will be between 2.5 and minus 2.5 volts. So we have differential voltage here, which is used for communicating on the CAN bus. So this transceiver here handles this conversion, and it also provides some protection and can, of course, and is crucial to have in a CAN bus. Okay, so here we have the CAN 1 silent and CAN 2 silent pins, which are controllable by the microcontroller. So in our case, we won't be using it, but you can look at the datasheet for more details. Then each of the power pins here needs its own decoupling and bulk capacitors according to the datasheet. We have the VIO pin, which is the digital voltage. So you have to really pay attention to the version of your chip. So in our case, we are using the HGVD version. And if you look at the order information, so let's type HGV. So if you type HGVD, you can look at the different the differences between the different chips. And the HGV Q1 has 5 megabytes flexible data rate, so this is what we want, CAN-FD, and it also have a 3 volts level shifter integrated. So this is necessary in our case, so that we can have use the 3.3 volt signal from our microcontroller. And it will also need an input for the 3.3 volts and an input for the 5 volts. So this is the same for both circuits, so I will not explain this part again. So now let's move on to the next circuit. Okay, so I've now explained the 3 first sections here of this board, so we'll now go into the flash memory section. So the flash memory communicates through the QSPI bus of the microcontroller. So this chip here is just an external flash which has 128 megabits of flash memory. So it's a very simple circuit. We only have a few components. So of course, as usual, we'll have a 100 nanofarad decoupling capacitor. This is used to have a local power supply, well-regulated power supply, to have which is used for decoupling the voltage on the VCC pin. And another important component is a pull-up resistor on the CS pin. So this is used, if you look at other circuits, you can see that this is used. This is to avoid some resets, like unwanted resets of the flash memory. So yeah, it's a very simple circuit. We only have each pin connected to the relevant pin on the microcontroller. And then it's only a matter of programming the chip, which I will explain in later in another video. So this is a fairly complex part of the project, programming the QSPI flash memory so that we can execute the program from the inside of that flash memory. So this is called XIP, or execute in place. And it is not a straightforward process. And yes, so I will be documenting this in another video. All right, so now we've gone through all of the sections on the left here, and we only have the node to hats connections to go for the schematics. So we can see here that the node to hats connections will take as an input for each hat an SPI bus, an I2C bus, and a set of GPIOs. So these hats, as I've defined before, are basically these connectors here. So they have the same shape on the 3 parts of the PCB. And if you look inside of that section here, we will have 3 circuits, and each circuit will take as an input the relevant buses. So the first hat will take the SPI1 and I2C1 and a set of GPIOs. So in our case, we want to have the different timers and also a UART section. And then the second hat will have, again, SPI and I2C, but it will also have UART, but this time with an RTS pin. So the RTS pin will be used can be used for other communication protocols. So for example, we know that for the USB to UART bridge, we only needed the UART RX and TX pins, but there are also other boards in the project where we will need another protocol like RS485 with the Modbus protocol, and this special protocol needs the RTS pin. So this is why we decided to break it out of the microcontroller and have it on this hat. Then we have the third hat here, which again takes as an input the SPI and I2C buses, and it also has dedicated ADCs. So this is just because we needed some pins, but we won't be using the ADC in this project. It also has an additional I2C port, which can be used for connecting multiple I2C peripherals on a single hat. So this can be used, for example, for the IMU, for having the magnetometer and the accelerometer and gyroscope on different I2C ports. But we in the project, in the Kerby project for the competition, we didn't use this I2C peripheral here. So now let's go into one of the circuits. So this is one circuit for the hat connections. So it's very easy it's a very simple circuit. We only have here the hat connector. So if you look through the symbol and at the footprint, you can see that this is our footprint, our standard footprint for each of the connectors. So you can see this here, and on the PCB, this will be the connector that I showed you before. So this is simply a standard socket, like female sockets that you will see on Arduinos and any other breakout development boards. So very simple type of connection so that it is very easy to debug. And then we have some ESD chips. So these ESD chips here are used for clamping the voltage so that we can always stay within safe values for the microcontroller pins. So this is a very fast ESD chip. So looking at the datasheet, we can see that it has a very, very low capacitance. So it has only 0.65 picofarad of capacitance, which means that it will be able to be switched at a very, very high frequency. And this is very crucial in our case because SPI, for example, is a fairly fast protocol. And it also has pretty good protection against different contact voltages. So this is what we use for our case. The only disadvantage, I would say, is that it's a very, very small chip. So if you look at the PCB, you can see this chip very close to the connectors here so that we can redirect all of the excess energy directly into that chip and then to the ground. So they are placed very close to the connectors, but you can see that they are very, very small. So it's not very straightforward to place and to solder, but it is not that difficult either. So this is what we use for protection of this device. Then we have 3 connectors for each hat. So these are this connector, this connector, and this connector. So you can see them on the PCB here. So this, and this is the same for all hats. So these connectors were not really used for the competition, but they are here just as a way to have a more modular system. So they are used, for example, if we want to have a PCB that is connected to this main board, but not through these pins. So let's say, for example, that I have a sensor that is delocalized maybe 10 or 20 centimeters away, and I want to connect it through I2C, then I could use this connector, for example. Well, I wouldn't recommend using I2C over long distances, but this is just as a way to have a more modular system. Okay, so we have also for each connector a 3-way jumper. So this jumper allows us to select between a 3.3 or 5 volts for the power pin of that connector. So this is just a jumper that you can solder on the back of the PCB. So we set it for each of the PCBs at the competition. We set it at 3.3 volts, which is where the arrow is here. All right. So yes, we also have this section here. So this is not very important. This is just for the bill of materials. So these connectors are not used on the PCB. You can see that I excluded it from the board, but not from the bills of materials. This is just so that the generated BOM will include the hats and the different components that we have for the hats. So in this case, it would be 2 times a 6 pins connector and 1 time a 4 pins connector. And we use just these components here to have a list of components on the bill of materials. Finally, we have the mechanical elements, the test points, and the logos. So there is nothing much to say here. We have the different logos, which have their their footprints here defined on the board, so you can see the different logos on the 3D viewer. So the different logos here, for example. And there are also some mounting holes and testing points. So the test points can be useful for checking for short circuits. So they are placed on the PCB at accessible parts of the PCB so that it is very easy to test. And we also have the mounting holes on the corners. So they are placed equally on a square. So it can be, so it's very easy to rotate the board to different in different ways. And then we have some other holes that are used for securing the hats to the main board. Here you can see that I've also placed an optional capacitor or an optional footprint. So this is in case we want to have chassis grounding. So let's say that we connect this mounting hole to the chassis of the rover. Then we might want to have a ferrite bed or a capacitor or some other network between the chassis and the ground of our microcontroller. So this is just another way to have to be able to control the ground path and the grounding of our whole system. All right, so now that I've gone through the whole schematic of the PCB, I now explain to you the PCB layout and what has to be known to really work on the project and how to use this PCB. So if you look at the PCB section, I will first explain the layout. So on the top here, we have the front signal layer. Then we will have two inner planes here. So we have the ground plane and we have a power plane. So this is not an ideal layout. Usually when you are working with four layers PCBs, you really want to have two ground layers at the middle to have a better signal integrity so that you have shorter current path from the signal to the ground layers. But in our case, it was much easier to route if we had a ground plane in the middle. So this is why we did it this way. And then on the bottom, we have another signal layer, which is also used to route some parts of the power. Right, so let's go through each section individually. So first, let's go to the microcontroller part. So if you look at the microcontroller here, you can see different parts of the PCB. So first, the decoupling capacitors are placed as close as possible to each relevant pins. So if you look at this section here, this 10 nanofarad capacitor is placed very, very close to the ground and analog voltage power pins. And then we have here a larger capacitor which is placed a bit further away from this microcontroller. We then have our ferrite bed and of course another decoupling capacitor. This is for our network. Then for the other VDD pins, as usual, they are placed as close as possible to the relevant pins. So in our case, we even use these polygon pores to have a very low impedance path from the pin of the microcontroller to the bypass capacitor. And you can see these capacitors all around the board. So let's select them here. And you can see them placed very closely to the relevant pins. So this here, and here. So yes, we have very, very close bypass capacitors, which is crucial in the design. Then we have the high frequency crystal and the relevant load capacitors. Okay, so now for the crystal section. So the crystals are routed in a way that is recommended by TI. So we have a load capacitor here in line with our crystal, and the crystals have their own dedicated ground planes, ground sections here, which are separated from the main plane, and they are connected to the main ground plane through a very short and thin trace at a single point. So this is a recommended layout by ST Electronics. and by TI or ST, I don't remember. We also have a guard ring around the crystal to really avoid noise coupling into the crystal. So the same type of routing was done for both crystals, so for the low frequency one here and the high frequency crystal here. Right? So now let's move on to the reset and boot section. So this is a very, very easy part of the routing. So you have a reset button here on the side. You have the decoupling capacitor between the pins. So this is, as I said, to avoid spurious resets. And it is then connected to this reset connector also, which then goes through the different lines here and through the reset port of our debug connector, which then goes through a series resistor for limiting the current, and then this goes to the microcontroller, to the reset pin of the microcontroller. So it's a very, very easy routing. Then we have here the ESD chip. So the ESD chip has to be placed as closely as possible to the relevant ports. So in our case, this is the debug port, and we have the ESD chip very close to the connector so that we can absorb all of the transient voltages and the excess energy that is sent into the chip. So I used a fairly large, or not very large, but a ground polygon here with two vias with no, of course, with no thermal reliefs to really absorb the energy back into the ground plane. Okay. So then we have, of course, the diode here for protection of this section of the board. So this is also connected to the ground and power planes through multiple vias for dissipating the power in an efficient way. Then we have the status LEDs and CAN FD bus status LEDs. So these are very, very simple circuits also. So let's look at it. So if you look at this, we can see that it is simply in line with the pin, goes through the resistor, then to the LED and to the ground. And it's exactly the same for the different LEDs here. And for this part of the CAN FD status LED. So you just need to take care to solder the LED in the correct orientation when you receive the boards. So you can see here the LEDs on the board. So you have one here and one here. So this is the yellow and green LEDs. And we have the status LEDs for the CAN bus. Then this is pretty much done for this section. Oh yes, we also have this dip switch. Also very simple circuits. So we have pull down resistors and series resistor for limiting the current. So they are very, very easy to route. We have just the trace that goes here, and then through the dip switch, and then we have a pull up resistors, pull down resistors to ground on this side of the dip switch. Okay. So this is it for the microcontroller section. So very easy section. There isn't a lot of constraints. So as I've said, the main constraints when routing the microcontrollers are to have the bypass capacitors as close as possible to the microcontroller with low impedance traces. So you can see that I've tried to increase the width of the trace as soon as I go out of the pin. And another critical part are the crystals, to have it fairly close to the chip. It doesn't need to be as close as these bypass capacitors, and to have dedicated ground sections for noise decoupling. And yes, that's pretty much it for this part of the microcontroller. And oh no, I almost forgot about the I2C pull-up pins. So these are placed fairly close to the microcontroller, and It doesn't need to, but we placed it close to the microcontroller because we wanted the pull-ups here to be connected to the dedicated ground plane that I will, the dedicated power plane that I will explain in the electronics fuse section, right? So this is it for the microcontroller part. So now let's move on to another section. So for example, the USB to UART section. So let's look first at the USB port. So the USB port is placed very close to this mounting hole, which is not ideal, but in practice it works. It's very, very, very close. And then we have the D plus and D minus, so the data lines of the USB going straight into the ESD chip. So we have a differential pair here, which is symmetrical to keep the same length. The width of the trace and spacing between the trays was chosen such that we maintain a certain impedance. So in our case, we maintain a 90 ohm differential controlled impedance using this norm here. So the GLC 04161H7628 layout here, I don't know how it's called, but this is a Stackup that is used by GLC PCB. So if we type this on Google, you can see that we will find the controlled impedance section of GLC PCB, and the Stackup for this special Stackup will is defined by this physical properties of the PCB. And for the USB pair, we want a 90 ohm differential pair, and we can calculate the width between the trace and the width of the trace using the GLC PCB controlled impedance calculator. So this is a fairly easy. So if I look, if I just type control GLC PCB controlled impedance calculator, we will find this page here, and we just define the number of layers, the PCB thickness, and the weight, and inner weight, outer weight, and so on. And we also need to, I don't know where the section is for, like if I type differential pair, for example, and I want 90 ohm, I can compute it using the GLC 7628 standard. And with the 90 ohm differential pair, this is a differential pair. We are using it on the top layer. The trace spacing here, this is a spacing that we choose. So in our case, let's look at the design rules and the design parameters. So I just opened this section here, and then in the predefined, in the net classes, for the USB, I chose a differential pair gap of 0.15 millimeter. And so now, let's say that we will, so as I will set it to millimeters, and after setting it to 0.15 millimeter and recalculating it, it will give me a trace width of 0.2395 millimeters, which is exactly what I put here for that trace. So this is a controlled differential pair, controlled impedance differential pair. So it then goes through two vias. This is just for inverting, like having the D plus on the left and the D minus on the right. So it is still routed as a differential pair, very close to each other while keeping the same impedance. We have a small curve here. This is to be sure that the two traces have the same length. And then it goes through a last set of vias to the USB to UART chip. So you have to make sure that we have the same number of vias between the D plus and the D minus, because the length of the track will be defined also by the thickness of the PCB if we use vias, because we will have a transition between two layers. and the thickness of the PCB will be added to the length of the trace for each transition. So then for the USB to UART part, it's very straightforward. So we have again the decoupling pins, the decoupling capacitors very close to the chip. So if I look at these capacitors here, we can see that they are very close to the chip. And then we have some other sections like the LDO here. And the LDO is connected to the USB 5 volts input. It then goes through the first decoupling capacitor to the VBus rev. This is the power input of our linear dropout regulator. We have the two decoupling capacitors placed as close as possible to the input and output power pins. This is just an enable pin, so it doesn't need any current or it doesn't need high current, which is why we use a very small trace. And then the 3.3 volts here just powers the chip. So we use a fairly large trace just in case with a power polygon. A power polygon here. Okay, so then we have all of the other like resistor dividers and stuff. This is just we just placed it fairly close to the chip to have something that is easy to route. It then goes. We then have the UART signals here, which go out of the chip and all the way onto the microcontroller. So here and to the microcontroller. So it's a very easy circuit also, and very straightforward if you look at the data sheet. Another part of the PCB here is the reverse polarity protection and the diode and the fuse. So let's first look at the fuse. The fuse is placed as close as possible to the connectors again. So this is not very crucial either, but so this is just for convenience. So we have the VBus, which goes through the fuse, and then from the fuse it goes through the diode. So we have here the bidirectional diode, which can really protect against transient voltages. So it goes through that diode, then goes through the MOSFET for protection. And here we have the protected voltage, which goes to the LDO. Okay. So this is it for the USB to UART section. So now let's move on to the power connectors. So first, let's look at this connector. So this connector here is, as I said multiple times, connected to this PCB here. And on this PCB, we can see that I have two dedicated pins for each power, so for the 3.3 and 5 volts. So this is because each pin can output 3 amps, like the maximum current that can go through each pin is 3 amps. So by using 2 pins, we can have 6 amps, which is way more than we need. So 5 amps, the 5 volts rail here can be used at around 2 amps. So this is the output of the buck regulator. And the 3.3 volts here can be used at around 1.5 amps. So we have here the different power pins. They are then connected to to the power path and the electronics fuse section. So let's look at the power path section for the 3.3 volts. So if you look at this is this section here. So we have here one of the inputs, which is so we have the 2 inputs. So the first one is the VX input, and the other one is the VIO input. So the VIO input is just the output of the LDO. So it's a fairly thin trace because there isn't a lot of current. Whereas the VX pin here has 4 vias that goes to the VN1 pin of this chip. So if you look at the trace, we can see on the other side that it goes through this with multiple vias, and then through the power connector. So this is a fairly high current trace. Okay. And then we have, of course, the MOSFET and the different resistors for that MOSFET, and the decoupling capacitors on the output and on the input of the chip. So it's a very easy circuit again. Something to take care of is to have power polygons that are as wide as you can as soon as you go out of the chip, so that we can really have high power, the highest current capabilities for the chip. So the same type of routing is done for the 5 volts part. So you can open this like this. And this is very similar. So we have again 2 sections. So we have here, this is one of the inputs which goes through the 5 volts input of the chip, so Vin1. And we have the VBus rev here, which is Vin2. So the VBus rev, as if you remember, is the protected output of the USB voltage. And then the output goes through a very wide trace. So if you measure the width of that trace, it's around 2 millimeters, or maybe a bit more, like 2.5 millimeters, which is way more, or not way more, but it's enough for the amount of current that we want to have. So it then goes through the different 5 volts parts of our circuit, of the system for the hats. So through the 5 volts port of the hats here, and the 5 volts of this hat. So if you look at the hat again, but I will explain it in the hats section, we have 2 pins for the power for the 5 volts and 1 pin for the 3.3 volts. Okay. So, all right, so now let's look at the 500 milliamps fuse section. So this is the fuse section. It's located a bit higher up on the board and fairly close to the microcontroller. So we had it pretty close to the microcontroller because we wanted to separate the microcontroller power plane from the global power plane. So let's look at this part of the system. So here we have the chip, and all of the routing is done according to the data sheet, or so according to the recommendations of the routing of the data sheet. So if you look at the end of the data sheet, you can see some routing examples usually. So this is an example, for example. So yeah, there are multiple examples of how to route the chip, and we just base our own way of routing from that example. So in this case, this is not the right package. So there might be other examples. And you can also look at evaluation boards. So for example, if I type TPS 2125947 evaluation board, you will find this website here. So this is the evaluation board, and then you can find some more information. So if you look at the technical documentation, maybe, I'm not sure, but no, this is the data sheet. Now, if I look at the evaluation module, here we will have an example of layout for the chip. So we also looked at this layout in order to do our own layout, so that we can have something that is as close as possible to something that was verified to work. So it's not very complex again. So we have multiple vias for the input power and the output power to really have high, to be able to accept high currents. And then the different capacitors, the coupling capacitors, the resistors and such are placed fairly close to the pins. and we use power polygons, polygon pores whenever we can, so that we can have a very good control over the shape of the different traces. So the output of that fuse is connected to the microcontroller, and you can see that most of the peripherals, like the I2C pull-ups, are also connected to that power plane. Here you also have the QSPI Flash memory, which power is also connected to that power plane. Okay, so now let's move on to the node-to-node connectors. So the different microcontrollers communicate through FD-CAN. So now if I select all of this and look at the routing, you can see how it's routed. So we routed the CAN bus as a differential pair, again, as a length matched differential pair. So here we have the two connectors. The pinout of these connectors were done such that it follows the different layout, the different pinout for other parts of the system, because we also have a motor controller PCB, which is based on the Maxon motor controller motherboard, and it also uses this type of connector with this type of pinout. So we followed this layout so that we can have some compatibility between the cables and between the different parts of the system, so that we don't accidentally plug something into another and it burns. So this is why we chose this layout. So here you can see that the CAN high and CAN low are routed as a differential pair. It goes through the other connector because we want to be able to daisy chain the board. So we have two connectors. It then goes through the ESD protection chip. So it's very close to that connector, directly going into the pins. We have two vias for dissipating the power to the ground plane. So then we go through this differential pair. You go through the decoupling circuit. So here we have optional decoupling capacitors. Here we have the capacitor for the terminal, the split termination part of the circuit. And then it goes through this switch here, which can be used to activate or enable or disable these termination resistors. It then goes through two vias. So this is for switching between the CAN high and the CAN low, so that we can have the CAN high on the left and the CAN low on the right. We have here again a small loop for matching the length between the two traces. It then goes through the common choke filter and then directly onto the transceiver. So after the transceiver, we have the TTL voltages, which are connected. So the 3.3 volts voltages, which are connected to the microcontroller for communicating through the FD CAN bus. So the other side is done very similarly. So we have the trace here that goes through the two connectors, ESD chip, filtering circuit, SPDT switch, common choke resistor, and transceiver. You can see also that I placed a lot of vias around the traces. So it might not be very useful, but this is a way to do what is called via shielding, and it allows us to try and keep the noise at this part of the circuit and not have it dissipate through the whole circuit. Okay, so now that we've gone through these three parts of the design, let's go to the flash memory part. So that there isn't a lot to say here. It's simply a chip, a flash memory chip, which is placed quite close to the microcontroller. We just connect directly the pins to the relevant pins on the microcontroller. We have the decoupling capacitor close to the power pin again, and just the pull-up resistor on the CS pin of the chip. So very easy routing, nothing much to say here. So now let's move on to the next part. So then the node to HATS connections. So I will just explain one of the HATs, for example, this one. So here we have the HATs. The HAT connector is comprised of these 6 pins here, these 6 pins here, and these 4 pins here. So the shape of this connector is the same for every part here. And this allows us then to connect PCBs which have the same shape here so that we can have a very modular system. So these connectors here and here, they first go through the ESD protection chip. So this is a chip that is very close to these pins and allows us to protect against transient voltages. And then it will go through the whole board and maybe through these connectors first, yes, for delocalizing some connections if we need. And then it just simply goes through the whole board to the microcontroller. So a very easy way to route also. I mean, there isn't a very complex circuit. It's all about routing. A very important thing to note when routing is to keep the traces as far apart as physically possible whenever you can, so that we don't have any crosstalk or noise propagating from one trace to the other. So that's it really for the different hardware parts of that circuit. So we then have, of course, the silk screen. So I've decided to remove all of the reference designators like C1, C2, R1, and so on, so that we have a cleaner PCB. We have some layouts here and some drawings on the back. So all of the pins have their function, main function, and pin number just next to the pins, so that it's very easy to debug. We have here also some reference for the test points, so it's a very easy to use board, and I think you will be able to get a very good hang of it in a short time. Okay. So now let's just have a small look at the 3D model, just so you understand what is what. So just as a reminder, here we have the USB port. This is an external reset connector that can be used instead of this one. So we will be using this one most of the time. I've never used this one actually. So this connector here is connected to an ST-Link, which is an external debugger. It could also be connected to a G-Link, which is also another type of external debugger. So this is the debugger that we will be using mostly. Then we have the power connector here for the external PCB, which provides high power input voltage and input current. And here we have the different HAT connectors, which are connected to different PCBs. We will have some spacers to secure the HATs in place. Then we have the node-to-node interconnects, which communicate through FD CAN bus. So this is CAN 1 and this is CAN 2, which means that we can have one board like this, another board underneath, and we can connect it, daisy chain it. So we have one connection here, and then this connection here is connected to the other board, and so on both sides of the board. And here we have some connectors which are connected to the I2C, SPI, and some of the GPIOs here for this connector. Then we have the termination switches. So if the switch here is towards the TRM silk screen, so the TRM text here, it will connect the CAN bus to the termination network. And this means that it will terminate the bus. So we only do that on the first and last node of the FD CAN bus. So in our case, it would be the Jetson would be the first node, and the last node would be the last node in the network of the FD CAN bus. Right, so then we have, of course, a reset button here. So this is not very easy to access, so you will need to use your little pinky finger to access it and press it. Here we have the switch, so you have to make sure to always set it in the FM mode, so this is the firmware mode, and not in the bootloader mode, or the program will not be working. So I set it just in case someone wanted to write a custom bootloader section and have something very complex. But in our case, we will not be using the bootloader mode. Then we have the dip switch here, which is used to set the ID of the board. So it uses a binary concept. So if I have everything set on the right, it will be simply 0 for the ID. If I set this one, it will be 1. If I set this one, it will be 2. This one will be 4, and this one will be 8. And we can have up to 16 different IDs, so from 0 to 15. In our case, we don't want to use the ID 0, which is dedicated to the Jetson. Okay. And yeah, so that's pretty much it for the different connectors and the different peripherals of this PCB. So now you will see in the next videos some more explanation about the power board and also about the different sensors and HATs that are connected to this main PCB.